Okay, so let's talk about rotational dynamics. Remember, dynamics, when we did dynamics before, is when we had things that were accelerating. Now we're going to have things that are rotationally accelerating, and think and talk a little bit about those. Specifically, we're going to introduce a new term called the moment of inertia, and that's a really important concept in rotation. So, first though, let's talk about just kind of a cool static equilibrium scenario, just to kind of think about how amazing your physical body is, especially your arm. Now, if you think about your arm has a bone that goes out here, right? And you want to hold something, so maybe you're carrying a bucket of water, so you have a force that's applied in this direction. That is going to create a torque that's going to tend to want your arm to rotate, but you don't want your arm to rotate, so you want to hold it there. So you need to have a force to overcome that desire for rotation. In other words, you have to have a sum of the torques equal to 0. So while you have this force, and here's your angle, right? This force is causing it to rotate this way. You need another force that acts in the other way. Here's the hinge, okay, of your elbow. So what do? You have a force right here that causes like a counter rotation. And you have, well, that's kind of the main one, right? So you have a force here and you have a force here. And the sum of the forces, this is going to cause it to rotate that way. And this one causes it to rotate this way out here. So the sum of the torques is going to be equal to 0, which is why this is such an important muscle, right? Ooh, look at that guy's muscle. That's such an important muscle because it has to have so much force since the lever arm is so little. This has a great big lever arm, so pretty good force. That's really, really hard to carry. This muscle has to be able to provide really, really large forces with really small moment arms. So I just think that's pretty neat if you think about what's going on with your arms. If you want to be a doctor, you have to take a lot of physics because there's so much physics going on within the human body. It's pretty cool. Okay, so here's a practice problem. You saw this picture once before. You have a 400 Newton child and a 300 Newton child sitting on either side of a 2-meter long seesaw. Where along the seesaw should the pivot be placed to ensure equilibrium? And it says disregard the mass of the seesaw. That becomes a lot harder if you have to think about the mass of the seesaw. So we're going to ignore that. It's not going to be this seesaw because this has a lot of mass. It's going to be a super lightweight one, and where the forces of the people are much more compared to the force of the seesaw. So here's the problem. I have a seesaw. I have 400 newtons in one direction, and I have 300 newtons on the other end. So 400 newtons on one end, 300 newtons on the other end. And the question is, where are we going to put this fulcrum, okay? The little balance. Where are we going to have it positioned so that the two people are equally balanced? Obviously, this picture has it in the middle, so in order for them to be balanced, you'd have to move it closer to her, right there. The question is, how far? Well, if the whole beam is 2 meters long, and we have these forces, now we're going to do a sum of the torques to figure out where can we put that fulcrum so the sum of the torques is 0. So remember, if we're doing equilibrium problems, that's just FD cosine theta. I'm sorry, FD sine theta, a mistake. And in this case, the sine of theta is 90, or theta is 90, so the sine of theta is 1. So here's how we lay out the problem. Now let's think about what I just did there. I had said 400, okay, 400 times x. X is the lever arm, right? So it's force times a lever arm. Okay, now let's think about the direction that's going. That's going to cause the rotation to go counterclockwise, which is positive, which is why I have a positive 400x there. And then I have minus 300. Okay, so the 300 is right here. And the lever arm, in this case, well, if this is x over here, then this is going to be 2.0 minus x. That's the lever arm over here. So 300 times 2.0 minus x equals 0. Now notice I put a minus here because this tends to torque it in the clockwise direction, which we've agreed is negative. So let's get rid of those so you can see what's going on. And let's complete the math, and we get 400x minus 300x, and I just took the minus 300 times 2 and moved it over, and I solved for x, and I got x is 0.86 meters. And so it's 0.86 meters from the one person and 1.14 meters from the other person. So there you go. Okay, now moving on to talk a little bit about dynamics. Let's remember back to Unit 2 where we talked about Newton's laws, and specifically Newton's second law, which is F equals ma. In other words, if you apply a force to something, you are going to get acceleration. Now, the question is, if you apply a torque to something, then what happens? The answer is you're going to get rotation in the form of angular acceleration, alpha. Remember, alpha is the Greek letter that represents the angular acceleration as something rotates around faster and faster and faster and faster and faster. So, F is proportional to A. Okay, force is proportional to A. And otherwise, you apply a bigger force, you get a bigger acceleration. Torque is proportional to angular acceleration. Bigger torque, bigger angular acceleration. But there might be something in there that makes it a little harder to get it to accelerate. In the case of a linear translational motion, you have F equals ma. M represents the inertia of an object. So if you want it to accelerate, if you have a little bit of mass with the same force, you can get a great big acceleration. But if you have a little teeny mass, if you have a great big mass, then you're going to have a little acceleration for the same force. So the acceleration doesn't just depend on how big the force is, it also depends on how big the mass is and how hard it is to push it or move it or pull it or whatever you're going to do, accelerate it. Is there a similar type of a dynamic when you're talking about angular acceleration? In other words, if you apply a big torque, you're going to get a big angular acceleration. Is there some factor that's going to depend, that's going to help you understand whether you get big or small acceleration? The answer is yes, there is. And it's called the moment of inertia. And we designate it with the letter I, capital I. And so we'll just talk about how you define that. So just to kind of keep with our analogs, right? For equilibrium, the first law said if the sum of the forces is equal to 0, then, if the sum of the forces is equal to 0, then we have equilibrium. If we have sum of the forces equals mass times acceleration, we call that dynamics. But then we have the analogs with torque. Sum of the torques equal to 0, we call that rotational equilibrium. So we set up free body diagrams, we solve for missing forces and stuff. And then rotational dynamics, torque is proportional to sum of the torques proportional to alpha. So this torque will cause an angular acceleration. Okay, inertia. We have talked about this before. Mass. Mass is how we quantify inertia. It is harder to get to moving, it has more mass. We quantify inertia with the unit of kilogram in SI units. We say that mass is an intrinsic property. In other words, it doesn't change. If you're here on Earth, your mass is the same as if you're on Saturn. If you're out in Venus, you're out in the middle of space, your mass is the same everywhere. Okay? Now, with rotational inertia, we talk about the moment of inertia, I. It has units kilogram meters squared, which gives you a hint of how you might be calculating the moment of inertia. It is going to have a mass term and a meter squared term, so a length squared as part of determining what it is. That's why it's kind of hard. This is not intrinsic. It depends on the axis of rotation. Well, what does that mean? Something might have a small moment of inertia if it's rotating in one way around one axis, but they might have a much larger moment of inertia if it's rotating around another axis. So if you think about a rod, and if I spin the rod here around its center, okay, so this one has the rod spin around its center, it spins pretty quickly and easily. But if you want to spin it around its end, it's like whoop, whoop, whoop. It's a lot harder to do because there's more mass out here further away from the axis of rotation. Out here, the mass is pretty close to the axis of rotation, right? Because that distance gets greater, and because you see you got this square term in here, that mass being further away from the axis is going to have a really big effect on how easy it is to get it to rotate or spin. So, when you think about moments of inertia, think about resistance to rotation. If something has a large moment of inertia, it does not want to rotate. If there's a small moment, it'll rotate a lot easier. Here's the key. The more mass that is farther from the axis of rotation, the larger the moment of inertia. In other words, the harder it is to get it to spin. So, this guy out here, to get it to go at the same angular velocity, it's going to require a lot more torque. Okay? This guy out here, moment of inertia is closer. It's easier to spin. Okay? So, like F equals ma. The bigger the mass, the less acceleration you get with the force. With the moment of inertia, the bigger the moment of inertia, in this case, the less it's going to want to accelerate in the angular direction if you apply a torque. Okay, we have some cool demos you'll have to check out when we are in class. Okay, let's keep moving. So this is a little chart that shows you moments of inertia of some familiar objects. So if you have a rod, this is one I just showed you, if you have a rod at the length L and a mass M, and you rotate it around its center, okay, so you rotate it around its center, its moment of inertia is 1/12 ml squared. If you want to take the same rod and you want to rotate it around its endpoint, it has a moment of inertia of 1/3 ml squared. And if you know your fractions, then you know that 1/3 is 4 times as big as 1/12. Okay, now check out the spheres, right? So we got my spheres here. In this case, you have a solid sphere. So think about like one of those, a solid ball of chocolate, okay? If you want to rotate it around its axis, an axis that goes to the center, it turns out that its moment of inertia is 2/5 mr squared, where r is the radius of the sphere, m is the mass of the sphere. But if you have a hollow ball, a hollow sphere, okay, so here's a sphere that has the same radius, and it has the same mass, okay, so maybe it's a pretty dense type of mass, and it's all located at the outside, right? So this is like a shell, it's hollow inside. If you have all the mass on the outside, it has 2/3 mr squared. So that's a lot bigger. So you have a lot more inertia, or a larger moment of inertia, when you have all the mass out on the edge. And that should make sense, right? Because if you want to spin something around, if the mass is located close to the axis, it's really easy to spin it. But if all the mass is far away from the axis, it's a lot harder to spin. So you're kind of looking for a theme here. When you have mass far away from the axis of rotation, which is what you have in this case right over here, then it gets harder to rotate it. And then these are just some other ones. This is another common one. If you have a cylinder, this is a hollow cylinder or a hoop. So a hoop is has the same moment of inertia as a hollow cylinder. That's going to have a moment of inertia of mr squared. If you have, don't worry about this one, that's really complicated. We'll do that in advanced physics. But then if you have a solid cylinder, okay, that has the mass distributed evenly, and so it's not all located at the outer edge. It has 1/2 mr squared. So check out these two differences, right? If you have a solid cylinder, you have 1/2 mr squared. If you have a hollow cylinder, you have a full mr squared. So much bigger inertia here. Another thing to think about, it's not on this list, but you should know, like if you have a mass and you're attaching it to a string R and you're rotating it around, ooh, that was a terrible circle, it's rotating around like this, that would have a moment of inertia of mr squared. It's kind of a simple formulation. So just a point mass that is rotated around a center is going to have a moment of inertia of mr squared, and you'll need that for some of your homework problems. Okay, so before we talked about if you have a net force, you're going to have a mass, you get acceleration. In this case, we have, if you have a net torque, it's going to lead to your moment of inertia times your acceleration. Now, we're not going to solve problems with this type this year, but in the future, good to know. Like this is the analog to F equals ma. All right, they go together. Okay, here's a cool concept question. We're going to test this out in class. If you have 2-meter sticks allowed to rotate about one end on the ground, are released when they are inclined a few degrees vertical. Stick 1 has a large mass clamped to the upper end. So the idea is this. You have 2-meter sticks, and they're kind of leaning over, and you have one here, and you have one here, okay, next to each other. And this one has a mass at the top, okay? Stick 1 has a mass at the top, and the other one has a mass at the bottom, or close to the bottom, okay? And so you're going to drop both of them at the same time. And the question is, who's going to hit the ground first? Okay, they're both going to fall. Who's going to get the ground first? And I'm not going to answer that because you have to think about it, come up with an answer, persuade yourself, and then we'll demo that in class. Another fun demo we'll do in class, and here's what you want to think about. A solid cylinder, a hoop, and a solid sphere are released at the same time at the top of the ramp. The order of finish for the race at the bottom from first to last will be what? In other words, who's going to win the race? Think about which ones are easier to get down because they have less rotational inertia. Okay, in other words, they're going to have the same gravity. If you have a can, okay, and you have a can, and the can is on a ramp, okay, and let's say this is a hollow can, so all the mass is on the outside. Think of the fact that the center of mass is going to be right here, right? The center of mass is right here, and there's like this pivot point here. So this causes a torque. which is why rolling things rotate when you put them on a hill. Okay, so the center of mass creates a little torque. So in each case, we have the same type of idea where whether it's a solid cylinder or a hoop or a solid sphere, the center of mass is always going to be in the center, and so that's going to create a torque that causes it to rotate. So they're all going to get the same torque because they have the same mass. But the question is, which one is going to get to the bottom quickest? Okay. In other words, which one has the least inertia? Because the less inertia, the faster it's going to angular accelerate. So we'll do that in class 2 as a demo. But thinking about, take a look at these and figure out what you think the order will be. And then we have a final race, which is kind of fun, where we race an empty can, refried beans, chicken broth, evaporated milk. And the question is, who's going to win that race? So try to think about that and inertia and rotation and who you think will win the race. And we'll test that out in class as well. Okay, that's it.